Dzień dobry Państwu. Nazywam się Krzysztof Turzyński, jestem prodziekanem Wydziału Fizyki Uniwersytetu Warszawskiego. W imieniu władz dziekańskich chciałbym Państwa bardzo serdecznie powitać na dzisiejszym spotkaniu z serii Zapytaj Fizyka. Ladies and gentlemen, my name is Krzysztof Turzyński and I'm a Deputy Dean of the Faculty of Physics University of Warsaw. On behalf of the Dean, I would like to welcome you most cordially at this Ask a Physicist series. This is a series consisting of lectures happening in evening that are addressed to general public. And in our previous meeting, we met with the Nobel Prize laureate, Shuji Nakamura. And in 2 weeks, we'll be sending our audience to the outer space with a person familiar with the intimate details of the Rosetta mission. Today, we are going to offer you time travel with no way back. And to introduce our speaker, I would like to ask a person who is behind this series, Piotr Sułkowski.
Dzień dobry albo dobry wieczór. Przedstawię naszego gościa po angielsku. So, Professor Markus Klute is a professor at MIT, Massachusetts Institute of Technology in the USA. He did his PhD in Bonn at the University of Bonn, and then he spent several years at CERN, in Chicago also, and in MIT, and finally he became a professor there. He was involved in particular in finding Higgs Boson at the Large Hadron Collider at CERN, so you will have a chance to listen maybe some parts of this story from him today. He is also engaged in various science outreach activities for pupils from schools, and also he gave several lectures of this type in MIT, so I hope he will have a chance to compare the audience in Warsaw and in Boston, and then give some of his insights. So this is our pleasure to welcome him.
Good evening. Thank you very much for those kind words, the introduction, and the invitation to come here to Warsaw. I've been here first time in about 27 years ago, and just walking down the streets here, a lot of good memories came back towards this first visit. So today we're going to discuss nature, the secrets of nature, and I will describe how we are trying to unveil those secrets of nature. The title is rather ambitious, an outlook on fundamental physics in 100 years. A time machine. We'll see how much I can actually answer these questions or give you a real outlook, but I will pave a road in explaining how we actually go after these deep questions of nature. So let me start with this picture here. This is a very crude summary of the standard model in particle physics. It's very crude, but it's sufficient to give you a few general ideas and concepts. The first one is there's two different kinds of particles, the matter particles, or the fermions, and the force carriers, the bosons. There's three different kind of forces being carried by those particles: the electromagnetic force through the photon, the weak force through the W and Z boson. The weak force is responsible, for example, for the burning of the sun. And then this G particle here, the gluon, which holds together protons and neutrons. It's, by the way, also responsible for the mass of this table here. This is basically the energy stored in this gluon field, but I'm already getting too technical on this. So you see here, when you look at this, there's patterns. There's three of each type of those quarks here, or electrons. They come in three, we call them generations and families. The only difference between this up quark here and this charm quark and this top quark is the mass of the particle. And there is where the Higgs boson or the Higgs field comes into play. It's depicted here as something which is very, very central, very, in the middle of all those particles, underlying this theory, the Higgs field. Those particles, the up quark, charm, and the top, they require mass through a coupling to the Higgs field. So what does this mean? How can we think about this? So we have the Higgs field, which fills all of space. And you as a particle, be it an electron or a top, you travel through this space. you feel the space, you interact with it. And that feeling is an inertia, and this inertia is what we call the mass of those particles. So if you're an electron, you have very little interaction with this field. If you're a top quark, you have a very strong interaction with this field. Hence, the mass of the top quark is much, much larger than the mass of the electron. So very important here, this standard model of particle physics is actually a theory. It's a quantum field theory, and that means that those particles can be described as fields. More importantly, we can make calculations. We can calculate properties of interaction of particles. For example, a scattering experiment. We can build an experiment and make a calculation and compare those. We can test the theory with experiment, and we can make experiments and then confront them with the theory. It's rather important. It's rather important. If you look at this particle content, this is all known elementary particles. If you look at when we actually discovered them, this is summarized in this table. The first elementary particle discovered by J.J. Thomson was more than 100 years ago. And it took us some time, or us as mankind, I was personally not involved for sure, to discover the next particle, the photon. Albert Einstein was involved in this here very strongly. So, and then you see that there has been some progress after the Second World War in kind of the zoo of particles appearing and actually causing quite some confusion at times. It wasn't clear in how to explain those additional particles and what their meaning will be. Today we have a much cleaner picture and a much cleaner idea. But in my career as a physicist, we had 3 big discoveries, and only those last 3 years. The top quark, the tau neutrino, and the Higgs boson. And the Higgs boson, because of the importance of the Higgs field, is probably the most important of those 3 discoveries. You probably know that in 2013, the Nobel Prize in Physics was awarded for the theoretical discovery of this mechanism. This theoretical discovery of the mechanism happened in 1964 by Jean-François Engler, Peter Higgs, and others, and it took us a long, long time to discover these particles. From an experimental point of view, and I'm an experimental physicist, it's just very, very hard to produce those particles and then identify them with our detectors and differentiate them from other signatures which might look very similar. So in summary here, we have a very, very successful theory. It took a long time to develop this particle context. The theory was developed in the 60s, 70s, 80s, and so on. It took a lot of time, and it's very successful, and it actually describes most of the experiments, or all of the experimental data we have today. The other part of the story is cosmology, or Big Bang cosmology, or the standard model of cosmology. You have probably all heard about the Big Bang theory, if not just for the TV show. And from the TV show, you know that the universe is 13.7 billion years old. 13.7 billion years ago, the universe began with the Big Bang. There was a rapid phase of growth. We call this inflation, which is quite interesting because we actually don't know exactly how this inflation really works. There's one open question. Finding experimental proof that this actually happened. We can see that there's quantum fluctuation at that time are basically the seed for the creation or the structure formation of the universe. So 13.7 billion years ago, the seed was set in order to give the structure of the universe today. It took about 100,000 years for the universe to cool down and become transparent for light. And this is depicted here. It's not very visible here. We can measure this light today, and we can use this measurement of this light in order to see how the universe looked like at that point. Then further, the universe cooled down, and first atoms were created, and first nuclei, more complex nuclei were possible to be created. Our galaxies and stars are much younger than that. It took about a few hundred million years for the first stars and galaxies to form, and we are here 13.7 billion years ago, and we wonder how this all happened to be. Today, the energy matter content of the universe can be summarized with this pie chart here. There is 5%, about 5% of this energy matter content of the universe is what we understand. It's atoms, it's baryons, it's a matter like this table around us. Most of it is much less complicated than this table. And then there's about 25%, which is called dark matter. It's called dark matter simply because we cannot see it. In other words, it's called dark matter because it doesn't interact with this electromagnetic interaction. And then there's dark energy here, which is even more bizarre. When we study how the universe evolves, we see that it's accelerating. And it's accelerating faster than what we would imagine. Much faster than what we would imagine. So there has to be something like an anti-gravity which pulls the universe apart. And we simply call this dark energy. It's a catchy name, I would say. We don't know what this is. We don't know what dark matter is. We do understand this small fraction. So this is rather confusing and complicated. And those are the connection of those two things are the secrets of the universe we'll try to answer. How, with this understanding of the element of the smallest particles and the understanding of the largest scales in the universe, how can we bring those two things together and understand them together? So the story has to just somehow continue, right? This is the end. We discovered, the particle content of the standard model is complete. We can extrapolate this theory to higher energies without falling into some trap or a real problem. But I answer this question, and that I don't need a crystal ball for this, because of course there is new things to be discovered. Simply because of what I just told you, there is those secrets in nature, and that there needs to be an explanation for those. I'll summarize them here, but I go through them one by one on the next slides. So the first one is dark matter. So again, the matter we cannot see was first proposed in the 1930s by Oort and Zwicky. Zwicky was a Swiss physicist, worked most of his life at Caltech in the United States, and they looked at the velocity distributions of stars, and they found this is very inconsistent and cannot really explain it. And they proposed a solution by saying there's some more matter which we cannot really see, dark matter. This was later confirmed by Rubin and Ford. They studied the rotation of galaxies. This was already in the 60s and 70s, and they confirmed this, that there has to be some more matter. And you see this depicted here in this plot, which looks at the expected velocity distribution of stars from the visible mass distribution you can see. And then you just you make your measurements and you compare those two things, and you see that they're not in agreement. This is one experimental proof for dark matter, but there's many more ways to look for and see the gravitational effects of dark matter. And this is an important point. Our evidence for dark matter comes only from gravitational effects. However, the leading candidate now for dark matter is a new particle, a particle which has to be somehow weakly interacting. Weakly, not really in the sense of weak interaction, but with a very, very weak strength. So very weakly interacting. So this is, if we propose a new particle, we can build collider experiment, and we try to generate those particles, measure them, and look at their properties. We failed to do that. We have not succeeded in doing that. The second big problem is biometal asymmetry, or matter-antimatter asymmetry. When we look around us, we see one type of matter. Let's call it matter. We miss or we fail to see antimatter. If you produce, if you have some bunch of energy and matter are kind of equivalent, you can produce matter and antimatter at the same time. Simply by having a high energetic photon, you create an electron and a positron, for example. And when you count, you should expect a similar number of those. However, when we look out in the universe, we observe matter galaxy. We don't observe antimatter galaxies. So there has to be some sort of imbalance. The standard model actually allows this kind of imbalance to happen, but it's insufficient to explain our universe. So there has to be some sort of additional mechanism, something else which allows this to happen. And nature is our proof. We have our universe, we can look at it. It is not in agreement with our predictions here. So, oops, it's not good. Okay, And then the next big question is the one of particle masses. How do particles acquire mass? And here we made a breakthrough. So we discovered the Higgs boson. With the discovery of the Higgs boson and some additional measurements, we can now say that the W and the Z boson and also the top quark and the tau, they acquire mass through this Higgs mechanism I just explained. Or we haven't looked at this part here. We haven't really, we have no evidence that the charm quark or the strange quark, and mostly the particles which are surrounding us, the down quark and the up quark and the electron, this table here, not the mass of the table, the mass of the elementary particles in the table, that they acquire their mass through the very same mechanism. We don't know that. The next question is obvious. You look at this table here, you see those 1, 2, 3 generations. You see the masses. This is a logarithmic scale, which means that if you go from one number to the next, is an order of magnitude difference. You see that there is a huge spectrum. Okay, you ask, why is this? Why is the mass of the top quark so different from the mass from the electron? Is this just a parameter of nature, or is there some deep reason behind this? Okay, and then I broke this distribution here, and there are 6 orders of magnitude missing, and then we'll find neutrinos. We haven't even measured the mass of the neutrino yet. There's another interesting discussion, entirely different lecture. But what you find is that the neutrino masses are tiny. They are really, really tiny compared to the rest. Why is that? Do they have a different mechanism to acquire the mass? Or is the Higgs mechanism just there's a parameter somewhere, somebody dialed a parameter, and it's very, very small for the neutrinos? We don't know that. So it's that bad, or the questions are so deep, that a friend of mine, Daniel Weizen, he wrote a book saying, we have no idea. And the book came out just a few days ago. You can buy this. It's very entertaining. But I think he's wrong. Wait a minute. It's a catchy title, so I have to say. But wait a minute, because we know quite a bit. We have the standard model of particle physics. Again, it's very predictive. It has a finite number of parameters, 3 parameters. You measure those parameters. And when you measure those with one experiment, you can make predictions for others. And I give you here 2 examples. Bear with me. They are very technical plots. One is a cross-section. A cross-section is more or less the likelihood of a specific thing to happen in our collision. Right? It gives you some rate of events when you look at a specific data set. So we measured the production cross-section for 2 top quarks in our data, in proton-proton and proton-antiproton collisions, at very different center of mass energy. These curves here, the blue and the green curve, they show you theoretical predictions. And then we have a measurement, or an entire slew of measurements here for the different center of mass energy, and they're bang on. That means that we do understand something. We do understand at least how to make those calculations, right? Another very interesting plot is here a summary of measurements by CMS. It's one of the experiments at the Large Hadron Collider. And we look at different processes. And you don't need to read this. You can also not read it. But we have various processes we try to extract from our data. And you see always the prediction and the actual measurement. And they are bang on. There's some uncertainties. Things move around a bit. But they are bang on for all those different processes. So we do understand quite a bit on how to make those calculations and predictions. And this gives us great confidence that we do understand that there is a range of validity for our standard model. And it goes one step further with the Higgs boson. So the standard model does not only predict the outcome of scattering experiments, like I just showed you, but it also postulated the existence of a new particle and its properties, the Higgs boson. And it took us quite some time, as I said before, but we actually discovered this particle in 2012. This is a distribution of the other experiment at the LHC, the ATLAS experiment. And it shows you, this is again just a count of events. You make collisions, you put them in some box, and you make a distribution where you just show the mass of some constituents we find in our detectors. And you find here that there are some processes in red, which we call background, and then there is processes in blue here, which look like our signal. And when we confront the data with this hypothesis of background and signal, I think you would agree that there is a signal. This is an indication that there's a Higgs boson in our data. So now this plot here is an entire slew of different measurements, all put together asking the question, do particles acquire mass through the interaction with the Higgs field. And then I'm simplifying. I know that there are some colleagues in the audience. I'm simplifying a little bit, but just a little bit. So you see on one axis here the mass of the particle, and on the other axis the coupling of the particle to the Higgs field. And I just show you those things are the same, which means in this plot they have to be on this line. And you see from our measurement, they are beautifully on this line. Okay? So we do understand quite a bit about this topic. So, however, as I started the discussion, this is not enough. There is this open questions, and now we have to try, we have to understand, and how do we make progress? How do we answer those questions? And that's basically what this lecture tonight is about. So, let me first explain to you what our experimental approach is. And I'm explaining this now for particle physics using collider experiments. I could give a parallel discussion for other parts of particle physics which are, looking for direct dark matter, and I'll explain this also a little bit. But let's look at what we do with particle physics as accelerator. So we study the interaction of those particles, of reactions, and then we measure the energy, the momentum, and the direction, and also the kind of particles we produce in a collision. We want to produce collisions at very high energies because this allows us to look really, really deep into matter. With our current experiments, the precision is in the order of 10 to the minus 18 meters, so very, very small. And that's basically the resolution power of our big microscopes. The big microscopes are our accelerators. So I show you here de Broglie, who did come up with this connection between the energy and the size of the resolution power of the matter you want to study. The next reason why we need very high energies is because high energies allow us to produce new states, new particles, which are very massive, like the top quark or the Higgs boson. We need a lot of energy in order to produce those particles and then look at their decay product in our detectors. And here E equal mc squared is probably familiar to many of you. There's another interesting part here. Boltzmann, the energy is related to the temperature. So when we produce high energetic proton-proton collisions or even collide lead with each other, we are able to produce matter which is extremely hot. Not quite as, but we can create an environment which is similar to the Big Bang. And that allows us to study a form of matter which is a plasma, meaning free quarks and gluons before things cool out, and then we look at the decay products again in our detector. The other part of the story now is that we want to build those accelerators. And this is one of the more technical things, but it's very, very simplified. The key parameters in the collider are its energies. So the total energy we call the center of mass energy. You just take one beam of an energy and another beam of the energy, and you can add them up, and you get the energy of the collision. And the second one is rather important. It's the luminosity. How often do we bring particles into collision? And this is shown here. We take typically a bunch of particles, let's say 10 to the 11 protons. On 10 to the 11 protons, we bring them in collisions. And then there's another factor here, which is the number of bunches. And there is about 2,000 in the LHC. So there's a lot of protons being brought to collision. When you bring them to collision, you have to make sure that they actually hit each other. This is shown here in those two sigmas. The size of the beam, actually, it's a few millimeter or tens of millimeter at the LHC. When you don't hit the two beams directly head on head, then you reduce the number of collisions you make possible to be analyzed. So you reduce the luminosity. When you make the beam smaller and you hit them head on head, you can improve the number or increase the number of collisions you make possible. And then collider works. There is some unit which accelerates the particle, and then there's a detector in the middle. You bring them into collision using focusing magnets. So we need units which accelerate, and we need units to focus. One trick is to recycle the particles. So we send them in a circular orbit to allow the particles to interact in more than one shot. If you have a linear collider here, you find that if you miss here, the particle is gone. You might be able to recover some of the particles, but that's very difficult. But if you have a circular collider, you can repeatedly accelerate, have them go in a circle, and then bring them to collision. If they're missed, maybe the next time they hit. Okay, so this is a summary of this discussion. There's quite a debate in the community whether or not you should build a linear collider or a circular collider. That's not what this is about. What I want to demonstrate here is that there's limitations to both. If you have a linear collider, right, you have individual segments in which and you have to build them after each other, which you use to accelerate. Each of the segments can only give so much kick to the particles, increase the energy so much. So there is a natural limitation. You can always make them bigger. But when this machine becomes 50 kilometers, then that's a really large machine. Similarly, for circular machines, I didn't tell you that yet, but when you ask an electron to go around the corner, it radiates a photon. This photon is called synchrotron radiation, and it decreases the energy of the electron. So tough luck. You give energy, and this goes around the corner, and the energy is gone again. So you have to make the ring big enough such that the corner is wide enough for the electron or proton or other particles to not lose too much energy. So there is a limitation based on the energy of the machine and how much you can kick the particles, what kind of size of machine you can. And rings also become large. If you have a ring 27 kilometers in circumference, that's very large. That's a Large Hadron Collider. If you go to 100 kilometers, those things are enormous. Okay, so this is a picture which displays what we do at the Large Hadron Collider right now. So I'm not looking into the future. That's what we do. We just today had the very first collisions in 2019. We call this stable beam, and then we can start analyzing those things. So we have those bunches of protons. There's a total of 10 to the 14th protons in each bunch. It's an enormous number. And then we find collisions of protons. We actually look at the collisions of the things which are in the protons. Because they are so high energies, what we are studying are the collisions of the quarks and the gluons, which hold the quarks together inside the proton. We study the collisions of those. And then we have our big camera, which looks at the collision and reconstructs what happens there. This plot here is similar to what it showed you before, the cross-section, the likelihood of a certain process to occur in the detector. This is, again, orders and orders of magnitude. And here is a mass scale. So it is, when you have proton-proton collisions, you have an arbitrary energy of center of mass between the quarks and the gluons, or the gluons and the gluons. And it becomes harder and harder to generate new heavy states. So this cross-section decreases when you go to heavier states. The other thing you see is here, the total cross-section is enormous, 10 to the 11th. If you want to produce a Higgs boson, the cross-section is in the order of 10. Right? So you have to produce, in other words, you have to produce 10 to the 11th collisions in order to find or generate or create one Higgs boson. That's why this luminosity number as a key parameter for accelerators is super important. If you just make one collision, the likelihood that this is a Higgs boson is 0. We will not find a Higgs boson that way. And then we have our cameras, and this is my favorite camera. It's my current favorite experiment. It's a Cms detector at the LHC. This is rather complex, and I don't want to go into any detail, but this detector is designed to every 40 million times per second to make a snapshot of the event and decide whether or not it's interesting enough, and then, 100,000 times per second, read it out and study it with some more detail. There's detectors in the inner part, which are used in order to measure the momentum of charged particles. There is detectors in the outer, which stop the particles in order to measure their energy. And then there's another part of the detector here, which is called muon detector. Muons don't like to interact very much. So they basically go out here, and they can be reconstructed here outside. If you find a particle out here, then we know that it was most likely a muon. There is this silver structure here, which is rather interesting. It's the magnet built in the world which can store the largest energy. The magnetic field is 3.8 Tesla, and it stores that much energy because it's gigantic. It's really, really big. This entire thing is about 15 meters high, 25 meters long. It's fantastic. And sorry to say, there was a huge opportunity to just look at it up to 2 weeks ago or 3 weeks ago. The next opportunity will be around Christmas next year. So we opened this detector, and I think we had 10,000 people down there over the break. It was fantastic. Just giving an opportunity to actually show this. Looks nice on paper or on the slide, but in reality, it's fantastic. Okay, so now we can bring electrons to collision. Those are elementary particles or protons, and I just told you that only the constituent come to collision. There's, certain kind of physics question you can answer with one or the other. I like to quote Sam Ting. He won the Nobel Prize for the discovery of Jape size, and is a colleague at MIT. Every event at a lepton collider is physics. Every event at a hadron collider is background. And that's motivated, if I go back, by this plot. Most of the events are things we are not really interested in seeing. You can also say all events are equal, but some are more equal than others. Those Higgs events, they are more equal than the normal proton-proton interaction. Okay, so now, in order to predict the future, we can look back in history. And I did show you already that it took us more than 100 years to discover all particles in the Standard Model. And most of them were discovered at colliders. And so we look here at about the last 100 years in collider physics. This axis here shows the accelerator beam energy. It's not really the energy of the individual particles as a function of time. And you see that there's this exponential growth here from about the 30s to the 80s. So about 6 decades of growth. And it was driven by continuous innovation. We made the accelerators better. We understood how to store particles, to bring them to collision. And this pushed the energy frontier, and it pushed the discoveries I just showed you, especially in the late 50s, 60s, 70s, 80s. So if you look at a similar plot, now I'll show you the constituent center of mass energy. This is really the center of mass energy in order to create, for example, a new particle. And here you see the hadron colliders and the lepton colliders. They follow 2 lines here very nicely. Again, this is logarithmic, so orders of magnitude improvements from the late 60s till about this plot is from 1996. Already then, it was clear that we cannot continue this trend. See, at this time, the future was the LHC, and the next linear collider, NLC, both were designed, discussed, and talked about, but not really built. And you see that they're not on the line. There was a machine on the line. It was right somewhere here. It was right on the line, but it was canceled by US Congress. They thought it's too expensive. And that already tells you where one of the big limitations are in our field. It's money. Building those big, beautiful experiments and accelerators is rather expensive. Okay? And there's also politics involved in this, leading to this cancellation of this process. But you see, another point to take away here is that there's 2 general directions. There's electron-positron or lepton colliders, and there's hadron colliders. And at that time, people often talked about the precision machines and the machines which are used for discovery, namely the precision machines when you have elementary particles interacting, and hadron colliders when you have protons, and there's this huge bunch of background you have to deal with. It turns out that those hadron colliders are actually precision machines. And it took, again, a lot of work, decades of work of theoretical inputs, improvement of analysis techniques, improvement of detectors to improve the precision of this kind of colliders. So by doing constant development, we were able to get more out of those machines than initially thought in many cases. So this is a picture of the Geneva area. This is Lake Geneva. This is the Mont Blanc here. This circle here is not the LHC. The LHC is about 100 meters under the surface. And there's 4 main experiments. And you saw a picture of CMS. You saw a result of Atlas. Those are what we call the omnipurpose detectors. Those are the detectors which were leading the discovery of the Higgs bosons. They are the experiments which we use and the energy frontier. There's 2 others, ALICE and LHCb. Those are more dedicated experiments which have a more focused physics question. So the first high-energy collision at the LHC was March 30th, 2010. And since then, the LHC was producing collisions really marvelously. So we increased, almost doubled the center of mass energy up to the now almost design 13 TeV. And you see here, this plot shows what we call the integrated luminosity. This is basically the size of the data set we can analyze. And you see last year was fantastic. You know, this curve is much larger than this one here by a factor of 2. Also, the center of mass energy is by a factor of 2 larger. So this allows us to look and try to use this data to answer the question I was describing. And we have looked. We didn't quite find all the answers yet. We found some interesting results. So. And then in 2012, we were able to announce the discovery of the Higgs boson. And I will not repeat all the logistics of this discovery, but this was fantastic for science because we got a lot of attention. We got a lot of attention. First, there was a big announcement at CERN and in Melbourne. In Melbourne, there was a large conference where we discussed those results. Science was discussed in all kinds of magazines. You see The Economist here, Giant Leap for Science. You find the Time magazine covering Fabiola Gianotti, who's today the general director of CERN, the laboratory where all this is happening. This is not the topic of today's talk, really. This is more the topic of next talk. How do we go from here? How do we go from this discovery? This is a roadmap for this LHC. You find here, this is again years. And what we plan to do here is we plan to further increase the center of mass energy a little bit and then take lots of data and more data and more data. When you look at it from 2038, that's already quite far in the future. Backwards at today, you would see that we already only collected about 1% of the data we want to collect with this machine. Only 1%. This requires, again, movements and progress in technology. One key ingredient for the LHC in order to get more data is to squeeze the beam more. This is a picture or a diagram of one of the focusing magnets. It's using a technology which is a superconductor, niobium tin, which wasn't available when the LHC was actually built. This was developed over years, over a decade, in order to find the material to be able to use material and make a cable. A superconducting magnet is nothing else but a cable of superconducting material, which is spun in a coil. Okay? And so this is basically done here. Making this cable out of this material is extremely difficult. It's brittle. It falls apart. You touch it, it falls apart. So you have to find a technique in order to make those magnets. We are already here. We have test magnets. We will be able to do this in about 10 years from now. We will be able to install those magnets. The field strength goes from 8.3 Tesla for those niobium titanium technology used in the LHC to this 12 Tesla for those focusing magnets. This is very, very, very exciting. And this is also the roadmap towards the next level of machine, because you can use this technology and drive it to higher field strength, and therefore then you use this magnet to bend the particles around the circle. You can accelerate them to higher energies and bring them to collisions. So the physics case here for the LHC, we don't quite increase the center of mass energy, but we take more data. So the physics case here is to make precision measurement at this hadron collider. This includes the Higgs boson. And because we generate so much data, we can look for very rare standard model processes, or beyond the standard model processes, new physics processes, and those processes might help us to answer the question. If we are lucky, it really depends on nature and us to keep working, we are able to make a discovery, and then we can start understanding this newly discovered particle. This would be hugely exciting. It's exactly what we do with the Higgs boson. We just discovered the Higgs boson, it's now 5 years ago, and we are measuring its properties and trying to understand what it all means. This is the immediate future for the hadron colliders, and it goes all the way to 2040. There's a number of proposals on the market discussed in the community for future lepton colliders, electron-positron colliders. One is called the ILC, the International Lepton Collider. The proposal is for 30-kilometer, straight line, 30-kilometer, linear machine where you bring those electrons and positrons to collisions. The center of mass energy here is not 14 TeV, it's only 500 GeV, but it's 500 GeV of constituents, of the energy of the constituents, the things we bring to collision. So this is rather interesting, and you can extend this by increasing the potential of the things accelerating and by also just making it longer, okay, up to 1 TeV. If you want to go beyond this, you have to change the technology, and one proposal here is called CLIC. I don't want to go into the detail. It's a very different kind of technology in how the accelerator components work. And here, this is a project which would be built at CERN, 50 kilometer long, and 3,000 GeV center of mass energy. And then again, those circular machines. One is a project discussed at CERN. It's called FCC, 100 kilometers around. That's enormous. And a similar project in China, where you discuss 50 kilometers, but there's also proposals for larger machines in China. There's one very, very complicated plot, and I was wondering whether or not I show this to you. There's real physics in this one here. This shows the colliding beam energy going from almost 0 here to 3 TeV, a machine like this. And this is the amount of power you have to invest per how many collisions you produce. Never mind the units, but you see that when you go for the circular machines, if you try to increase the center of mass energy, they radiate so many photons that you have to basically invest a lot of power, real megawatts of the size of a nuclear power plant, in order to make those collisions. So that becomes very, very unfeasible. And when you go to very high energies, you see that the only option would be a muon collider going to very high energies here. Okay, so a few more words about this future, because you want to see what's available, what are we thinking about, and how can we project into the future. Okay, this circular machine at CERN is being studied right now. There's an international collaboration has been set up to study the prospects of a proton-proton machine, like the LHC, an E+ E- machine, like the formerly, I didn't discuss this lab, there was a machine where the LHC is right now, using the same tunnel, and potentially you can collide electrons and protons. And that's interesting for other reasons, to study the structure of the proton, for example. So we want to do this in the next couple of years and figure out whether or not we want to pursue this as a community of particle physicists. It's very easy to make a transparency with this. This is gigantic. And I just wanted to show you this picture here, which is the same circle, this circle here, in this area. So this is Lake Geneva. It's quite big. There's an entire mountain in the center of this ring. It's called Mount Salef. And it goes here around in a circle, about, on average, 400 meters under the surface. So just taking the elevator ride is going to be fantastic, I have to say. All right. But in all seriousness, those things are expensive. And you can make a very simple diagram trying to optimize the cost of a machine like this. At fixed magnet technology, so you pick one technology and you want to build a magnet, the magnet costs a certain amount of money. The money is typically driven just by the material you need in order to build the magnets. Production and so on is not just such a big part of the total cost. You have to build a tunnel. The cost for the tunnel, not quite, it's just linear. You make it longer, it takes longer, or you have to buy another machine or rent another machine in order to build it. And at some point, you want to spend the minimum amount of money to get a collider at a certain energy. So you find this is probably a good point. It turns out that this line here, this tunnel cost line, really depends on where you want to build the tunnel. It's actually rather expensive to build a tunnel in Geneva because of the lake and the mountains and all of those things. If you would put this in Texas, for example, where this initial machine was proposed, it's much easier. Or there's many other places I could name, okay? And then there's the technology you can use. There's niobium titanium, there's niobium tin, and then there's this thing which is called HTS, high temperature superconductor. There is a big future here. And if you're thinking about 100 years from now, I'm very confident that we will be able to build this kind of magnets, meaning that we can get much higher field strength and build collider-worthy magnets in order to build smaller, more cost-effective machines, similar to the FCC-EE, the thing we're discussing here. Okay, so you can make a roadmap for particle physics which might look like this. So we have the LHC, started collisions, pointers out, started collisions in 2010, is running happily, will be extended by the high luminosity LHC all the way to 2038, maybe 2040. This shows the first year of physics. ILC or the Chinese machine are discussed with rather aggressive timelines. First physics in the 2030s. This machine here would be followed by a proton-proton machine. You want to operate this machine for 10, 15 years, and then you have to change the magnets, you have to change the accelerator infrastructure. For the FCC, similar, you can probably start building a tunnel in Geneva while the LHC is running, but at some point, you cannot operate those two things at the same time, and it takes a long time to actually get the price of the magnets down to a level where you can actually afford it. So here I put this in the order of 2040 as a start. Maybe you start with an E plus and minus machine, and you start physics for a hadron machine in the 2050s sometime, maybe end 50s. This machine then would run for 40 years, and so if you do the math now, we're almost at the 100 years time span. So this sounds very fantastic, thinking about what will we do in 50 years from now, and then for another 40 years. It's fantastic. It is fantastic, true. If you go back to the LHC, the first plans for the LHC were done in the 80s. People were sitting together, building collaboration, trying to raise money, trying to motivate people to work and do research, and setting all of this up. It took about 30 years, a little less than 30 years, for the LHC to produce the first collisions. It's not that different here. It's a very large-scale project. They demand a lot of R&D and research in order to get to a construction phase, and then we want to explore the physics of those machines. All right, enough of collider physics, at least for now. I come back to this. There's other ways to answer the questions. So dark matter was in the center of focus before. Dark matter, okay, let's say dark matter should come out of this picture somehow. At colliders, we collide standard model, and we want to produce dark matter. You could also just take the dark matter, which is everywhere, just flying through us right now, and see if it interacts with standard model material. So you have a diagram which goes down here, standard model with dark matter, and you see some effect on the standard model material, maybe some xenon, for example, and you kind of prove this way, indirect detection, that dark matter exists. There is another really, really fancy and cool experiment, and I mentioned Sam Ting before. He's also behind this one, this experiment. We have a particle physics experiment on the International Space Station. It's called AMS, and it's sitting there and happily collecting data. What this experiment does, it looks at the remnants of interaction of dark matter. So it goes this direction. It's called indirect detection, where you produce standard model, matter and antimatter, and you try to find out if you find any sort of evidence for dark matter. So this slide is to say that there is one trajectory, which is collider, but there's other trajectories which are also worth pursuing and which are being pursued. Those scale. So this is a picture of the so-called Xenon 1 ton experiment, which just released its first result. And this experiment here can be scaled. You can make 10 of those if you want. You don't even have to have one experiment, or you make one big one if you want, which can be 10 tons, can be 100 tons or larger. So this, again, the driving factor then at some point is cost and technology. The story doesn't end with dark matter. Neutrinos, I mentioned that the question of neutrinos are somehow special, right? They only interact weakly. They're really, really light. But we can study neutrinos over an energy range which is enormous. We can look at neutrinos out of cosmic accelerators. We can look at neutrinos being produced in our atmosphere. We can, again, use accelerators in order to produce neutrinos. We just dump matter into a block of matter, and neutrinos come out, and then we can study those. There's neutrinos that come from the sun. Those are for free. And maybe we can even find ways to look at neutrinos as a remnant of the Big Bang. So neutrinos are rather interesting and also help to answer those questions. And then there's an entire different frontier and maybe an entire different field of research which just came out a little bit more than a year ago with the first detection of gravitational waves. So gravity is not mentioned in the standard model, but rather important to cosmology. And what happened, what the LIGO collaboration was able to do, they saw for the first time effects of two black holes circling around each other, generating gravitational waves which then can be found and measured on this planet. There's other experiments, future experiments, which have more sensitivity and can look at different aspects of gravity or gravitational waves. Again, another different trajectory of research trying to answer the question I was pointing out. Okay, now prospects. Now I'm, very carefully explaining what I think we might know. Okay, and I'm very, very careful in this because there's experts in the audience, and I know this lecture is recorded. Okay, so the Higgs is one example, predicted in '64, discovered in 2012. Our knowledge today is that it behaves like this thing in the standard model. And our measurements have a precision of about 20%. This is all relative, depends on what kind of measurement we look at. We know it's spin 0. This is predicted in the standard model. We know it gives mass to the W and Z boson. We know it gives mass to the third generation. In 100 years from now, we will know this precision will go to 0.1%. So it takes a little bit of more physics background. This 0.1% allows us to test any sort of deviations from the standard model to scales of multiple TeV on the Higgs boson. That's very exciting. But maybe more exciting is the prospects to find or measure the coupling of Higgs bosons to the second generation and the first generation. This plot is rather complicated, but it gives you, for one of those machines, the ability to make a discovery of Higgs couplings to electrons. And you need a lot of data. This is 100 autobahn is a huge number. And you need very clean and very precise beams. And only if you can do this, you'll be able to make this discovery. However, we're discussing 100 years into the future, so you will be able to build a machine like this, and you will be able to run it. Why is first generation mass so important? The first generation particle we are interested in here is the electron. The mass of the electron is a parameter of our standard model, which might be given by the coupling to the Higgs field, determines the size of an atom. It determines our chemistry, right? It determines the evolution of the universe, if you want. And I think it's interesting to figure out how this particle acquires mass. There is a ton of models, this is the next line here, which predict not just one Higgs boson, but 2 or more. And it would be exciting to find them, and one of the core of my research is to find those extra Higgs bosons. I'm, if I put my money in the basket, finding new physics and answering this question through the Higgs boson or additional Higgs boson is, it's, again, where I put my money. Okay, one of those models, or one of those group of models is supersymmetry. In supersymmetric models, you need additional Higgs bosons in order to give mass not just to the standard model-like particles, but also to the others. So in a nutshell, when you have supersymmetry, is a symmetry between those bosons and fermions, those matter particles and force carriers. And as a result of supersymmetry, there's an entire zoo of additional particles. Now, we haven't seen them yet. So today's knowledge is a lot of theoretical work, a lot of experimental work trying to find those particles, and we can determine that supersymmetry must be broken. So what does that mean now? Supersymmetry broken means the masses of those particles are different from the masses in the standard model. We determined this by simply looking. We didn't see them, so supersymmetry, if it exists in nature, must be broken. That's what we know today. This plot here shows you another part of our knowledge. We know it's broken almost extremely because the masses in which we can exclude for those particles are extremely high already. It's about 1,000 GeV. That's 5 times heavier than the top quark. So those particles, if they exist, they're rather heavy. Or we don't quite understand this, and we need some more ideas. So a little bit more on supersymmetry. So we looked at this. Can we discover supersymmetry? So we used a number of our searches here, and we ask ourselves, with a certain amount of data we are going to collect, are we going to make a discovery? And the color code here is such that blue means we might have some evidence. Red means we actually make a discovery. So with a high Lumi LHC, we might find it or we might not. Right? Not all of those points here are actually dark. But with the next generation of hadron colliders, the mass reach here goes from a few, maybe a couple of TeV, all the way to 20 TeV for some of those particles. So there's an order of magnitude additional mass range, which would be able to just nullify those. So my prediction for supersymmetry is that I'm kind of very confident, hopefully, careful with my words. I think that we will discover supersymmetry already earlier than this. Okay, dark matter, this huge question. The next example. Proposed in the 30s, confirmed in the 70s. Today's knowledge is that dark matter, if it's of particle nature, is very, very, and I should add very, very weakly interacting. It's not interacting like the W and Z boson or to the W and Z boson like other particles. It's much weaker. So again, here's one of those plots, mass and some likelihood. And this is a very small number. The cross-section in square centimeters here, 10 to the minus 45. This is the latest result, came out a few days ago. And it's super impressive. At colliders, we can give this kind of results. And you have to carefully look at those numbers here. And the plots, this is almost this curve here. You see that this low mass part here is excluded by colliders. And there's theoretical input needed in order to put those two things on the same plot. But we know the likelihood of dark matter to interact with our normal matter is extremely small. Okay, but we can bring this to the next level. The next generation, those next scaled version of those dark matter detectors, they will move this by another couple of orders of magnitude here. So I'm rather confident that in 100 years from now, we know if dark matter is a weakly interacting massive particle or not. Maybe it's just us not having the right idea and understanding gravity. Maybe there's other solutions to this question. We will also have answers to those alternative ideas. As I showed you, there's other alternative approaches to give answers or get answers to those questions. So this is a funny plot, which is rather old already, which gives you a landscape of possible beyond the standard model physics. Models and theories which can be used to describe and answer the question I was discussing. And it's fascinating because you find a large part of this is not yet thought of. And that's my favorite part out of this plot. We need to keep thinking. We need to keep understanding, using the data to teach us, nature to teach us, but also investigating whether or not we missed something. If you go back about 100 years, a little bit more than 100 years, Einstein, in a special relativity, just found out that time, there's something wrong with time. He started questioning this concept that time is some sort of invariant kind of thing. And lo and behold, he had very simply, actually, you can write this down on a few pages, or on one page, actually, developed special relativity, and then that continued into general relativity. All of this was not known before. And similar here, if we have new ideas, we might find theoretical answers to those questions, and theory then can be used in order to confirm and validate that. All right, so the last of this kind of slides and discussion is this one here. So I'm an experimental physicist. So this previous slide, I hope that my theory colleagues will help out. The exploration is what we do. And the parallel between Christopher Columbus and our discovery of the Higgs boson is rather striking. So the very first thing is that Christopher Columbus had a huge issue finding money. So he tried to raise money for his mission, and it was almost impossible. At some point, he was able to raise enough money to buy boats and ship west. Then he did this. So he discovered some, I should say, his objective was to sail west to reach Asia. He was driven by commercial needs and not by research. He was trying to find gold and pearls and spices. Okay, we have some different ideas of what we want to discover. And then he made a discovery. He found this new land. And he sailed around. He discovered the Americas, not America, and sailed back and reported and was celebrated. However, in his lifetime, he actually never figured out what he really had discovered. And that would be a shame if we would never figure out, by not looking, what we just discovered with the Higgs boson, trying to answer these other questions. All right. So with this, I conclude. And I have to tell you a secret. Typically, here I give you a conclusion in words of what this talk was about. But I find myself then just reading, because I'm a little tired already, not reading. So I give you the title of this talk, Unveiling the Secrets of Nature. So what I tried to do in this presentation was to show you first that there is very interesting and intriguing secrets of nature. And then I paved you some ideas, some directions which we use in order to unveil those secrets. How do we find answers? I gave you an outlook of fundamental physics. I gave you a roadmap for fundamental physics in the next 50, 80, up to 100 years, and some nuanced kind of examples of what we will know in 100 years from now. Let me make a few concluding remarks. So first of all, I go with Niels Bohr here. Making predictions is difficult, especially about the future. And it's good to mention here that in 100 years from now, will not be able to stand here to justify myself. So that's a blessing. The next point is, however, I showed you a lot of interesting results and evolutions in physics and understanding fundamental physics. And they are being pushed through technology, and they're being pushed by new and novel ideas. So in order to advance, in order to be able to answer those questions, we need to continue to do this. We need to continue to innovate and to invest. This has to do with money. This is really crucial. The continuity is rather important here. If we stop doing this, restarting an effort is extremely cost-intensive and difficult. And then the last point, which relates to the slide of Christopher Columbus, there's a spirit of exploration. It is really in the nature of fundamental physics that we do not know what's beyond our current knowledge. So we have to keep questioning what we know and try to find the next question and then the answer to those questions. So with this, I'll stop here and I'm open to questions. Thank you.